In this section we'll see how transformations change the shape of the graph of a function, and there are certain predictable changes that are made from given changes to the algebraic definition of a function. And we're also going to see how we can sketch a graph by breaking down the changes in the formula as successive changes of well-known types. And of course we can use our catalogue of given functions to find the graphs of a wide range of functions using this technique. The first thing we're going to look at are vertical shifts. So if we have a constant c which is positive, if we take the function f of x and suppose we add c to it, then the graph of the equation y equals f of x plus c is just the graph of the original function y equals f of x shifted upwards by c units. And likewise the graph of y equals f of x minus c is the graph of the original function y equals f of x shifted downwards by c units. And we can see why this works. The reason is because suppose x1, y1 is a point on the graph of the original function y equals f of x. Then we have y1 equals f of x1. And then we have x1, y1 plus c. This is a point which is vertically above it by c units, must be on the graph y equals f of x1 plus c, because we have y1 plus c is f of x1 plus c, and likewise we have a similar thing going on for f of x minus c. Let's look in particular at the function, the graph of y equals x squared, and how that's changed by adding 3 to the x squared and subtracting 3 from the x squared. And we can use our join the dots method from before. We have when y equals x squared, I'm going to use different color pens here so that you can distinguish between the graphs. So when y equals x squared, when x is minus 3, y is 9. When x is minus 2, y is 4. When x is minus 1, y is 1, 0, 1, 4, and 9 here. And now when I subtract 3, I get when x is minus 3, x squared minus 3 is 9 minus 3. And that's 6, but in particular it's the value I got here, minus 3. So the y value corresponding to this x value on the graph is exactly 3 points below the y value on this graph. Likewise, we have when x is minus 2, x squared minus 3 is 1. When x is minus 1, x squared minus 3 is minus 2. And when x is 0, x squared minus 3 is minus 3. When x is 1, I get minus 2. When x is 2, I get 1. And when x is 3, I get 6. And for every x value here, the corresponding y value on this graph is exactly 3 points below the corresponding y value on this graph. And likewise, if we add 3, then we should get that the corresponding y values are 3 points above the y values on this graph. So when y is x squared plus 3 and x is minus 3, then y is 9 plus 3, which is 12. But in particular, it's 3 points above the corresponding point on the graph y equals x squared. When x is minus 2, x squared plus 3 is 7, and it's 4 plus 3. When x is minus 1, x squared plus 3 is 4. When x is 0, it's 3. When x is 1, it's 4. When x is 2, 7 again. And when x is 3, It's 12 again. And let's draw all three graphs on the same axis, just to get a picture of how they're related. So we have our x values, pardon me, running from -3 to 3, and our biggest y value here is 12, so I'm going to make maybe 15 my highest y value here. We'll take blocks of 5 here on our axis. Okay, let's graph x squared as we did before using our join the dots method. We have 0 zeros on the graph, -1 and 1, and 1 and 1, so they're about here. 2 and 4 and -2 and 4, about here I would say. Might be a little off. And 3 and 9, and 3 and -9. So we get the bowl-shaped graph as we saw before. Could have sketched that without the join the dots method at this point, but I just want to illustrate a point here. Now for x squared -3, so this one is y equals x squared. X squared -3, when I take x equal -3, I get x squared -3 is 9, which is the y value in this graph, minus 3 points. So it's 3 points below, exactly 3 points below the point on the graph of y equals x squared. When I take x equal to -2, and the point on the graph here is 4 minus 3, which is 1, which is exactly 3 points below the point, the corresponding point on the graph of y equals x squared. When x is -1, we get -2 here again, it's 3 points below the corresponding point on the graph here. And I have it cuts the y-axis at -3, 3 points below where it cuts here. And I have when x is 1, y is -2, when x is 2, y is 1. And again I have the symmetry here, when x is 3, y is 6. And all of these points should be exactly 3 points below the corresponding point on the graph y equals x squared. Now obviously my scaling here leaves something to be desired, so they may not be exactly 3 points below, but they should be if everything is correct. So we see the graph of y equals x squared -3. Every point here for any given x is exactly 3 points below the corresponding point on the graph of y equals x squared. And similarly, for the graph of y equals x squared +3, every point here is 3 points above the graph of the corresponding point on the graph of y equals x squared. So when x is -3, this one is 12. Y is 12 here, so it's 3 points above. -2, y is 7. -1, y is 4. 0 corresponds to 3. 1 to 4. 2 to 7. And 3 to 12 again. So again, we get the graph of y equals x squared shifted upwards by 3 units. And so we don't have to go into this level of detail to sketch this graph. Once we can sketch the graph of y equals x squared, we just simply shift it upwards by 3 units or downwards by 3 units, depending on whether we've added or subtracted 3 to get the new graph. and that gives us a rough sketch of the new graph. I would like you to try to get a rough sketch of these three graphs using some of the graphs in your catalogue of graphs, and then look at the video to see if you've got the right answer.